All right. Good morning, Astro Chatters. Welcome back. We're excited to have you with us today. We've got a double header today. So we've got our conversation now. I'll introduce our guest in just a second, and then another guest this afternoon at 3 p.m. who will tell you a little bit more about towards the end of our discussion today. As a reminder, my name is Erica Wright. I'm your Youth Astronet Community Coordinator and host for today's chat. For those of you out there watching on YouTube, hopefully you'll join our conversation today. I want to remind you, you can ask questions on Twitter and on Facebook using the hashtag Astro Chat. I've really been enjoying you being part of our conversation, so please ask away. I'll feed them into the conversation where it makes sense. So let us know what you're curious about. Now, with that getting us started, I want to introduce you to our guest of the day, Jordan Eagle. Thanks for being with us today, Jordan.
Yeah, absolutely.
So I think today you're going to talk to us a little bit about Pulsar Wind Nebula, which sounds pretty exciting. But before we get started, I thought we'd talk a little bit about yourself. That sound good?
Yep, sounds great. Contrary to popular belief when it comes to really fancy titles like astrophysicist, I like to claim that I'm a completely normal person. Not at all, a genius that was just born this way. I was a very normal person, and actually growing up, I was really, really bad at science and math, like terrible. Always flunking those classes in high school, middle school, up into high school. And by the time I was a senior in high school, I was done with all of my math requirements. So I, did not even take calculus. I got a D in pre-calculus my junior year of high school. So I was like, why should I take a math if I don't have to? So I didn't. I never took physics in high school. I think even for the science elective, I think the science elective I think for us was physics, and I opted for oceanography. I was really just uninterested in school, and then I got into college. And I was having a good time with my academics. And so it just kind of occurred to me that if I want to do something that I'm really passionate about, it's probably not going to be easy no matter what it is. So I decided to just try physics. I was like, whatever, I'll test out physics as a major and we'll see how it goes. If it doesn't work out, it doesn't work out. You're like a freshman, sophomore in school. So you think that you have time to really think about what you want to do. So it was just testing the waters. And I really wasn't even good at it when I first started. I failed my first exam and I was super upset about it. But I wasn't really willing to give up yet. So I just kept studying. And I proved myself at the end of the semester. I almost pulled out with an A. I had a really, really high B. And that's really how it really started kind of snowballing, I guess. I kind of proved to myself that it really has to do mostly with work ethic and really just studying a lot. Because I was never good at math. So I was like, it just really takes studying to do this. So I ended up actually getting my bachelor's in physics, surprising everyone that knew me and even myself. And then I ended up getting into Clemson University to continue doing my research. So right after I finished bachelor's, I went into a PhD program there. And I had to work really, really hard there too, because I was coming from a small school. So I had very limited physics knowledge compared to a lot of my peers. So I was really behind on the curve. Again, it was not easy to do, but I persevered. And then eventually I got this predoctoral fellowship with the Harvard Smithsonian Center for Astrophysics. And so I've been here since January. And yeah, so it's been a wild roller coaster, but I wouldn't trade any of it for the world.
Sounds it. So I'm really curious, with being someone that wasn't quote unquote good at physics and math in high school, which that can mean a lot of different things, right? Like some of us think we're not good, but really we just haven't put the effort into it yet, or it just wasn't interesting enough for us to put the effort into it. What kind of made you shift into being interested? Like you said, I kind of went on a whim, but there's a million different things you could study in college. What kind of pushed you towards physics with you admitting to yourself being like, that wasn't my thing in high school? Where was that shift for you?
Yeah. So when I was younger, I always really loved astronomy and I didn't know much about astronomy. I knew I liked looking at the stars. Like every now and then me and my dad would go outside and he'd point out where all these planets are. I mean, we lived in the suburbs, so there was lots of tree line. So it wasn't like we had a spectacular view, but every now and then, we would go out and look at what we could see. And I did find that really interesting. But then once I got into high school, I noticed how bad I was at it. But I mean, like you said, though, it really wasn't about me being bad at it. It was me being uninterested and not really wanting to apply myself. I didn't care enough about it for sure.
I think a lot of people do.
Yeah. And I mean,
Not a common situation.
it's hard and it's not fun and you have to study for it. And honestly, I don't think I really understood what studying is until I got to college, if I'm being honest. But yeah, so I always had an interest in astronomy, but as I grew up in grade school, I thought that path was unattainable for me because of my experiences in those classes. But when I did get to college and I decided like this is something that I think I'd really like to do, so I'm just going to go for it and at least try. That basically was the thought process there. So
Great. Yeah. So like you'd had this, external pressure on you saying, well, that's just not for you because you haven't done well in these classes. But then you were able to take a step back for a moment and say, this is what I want.
yeah.
And kind of, if it doesn't work out, that's fine, but I'm going to go for what I want for a minute and give it a shot.
Exactly. Yeah. Like it wasn't like I was like, I'm going to cry myself in tears if I don't do well in physics. I was like, this is just got to try. If it's not for you, whatever,
Absolutely. Yeah. Give it a shot. There's no harm in doing that. You still have to take a lot of those some of those early classes anyways.
Yeah.
You can make it work in some way. So that's fantastic. And I think that's some good advice too, that if you're really interested in doing something, if you've got an interest in a science subject or, a subject outside of science, but you've always felt like maybe it's not for you because you haven't done great in the classes in school, to go back and give yourself a new shot at it, because there's a lot of different perspectives to it in college as well. The classes are very different from the way you learn in high school.
Yeah.
So I think that's a really great piece of advice for our audience out there.
I hope so.
Well, let's show them that you also do know what you're talking about. We can all say these things, but I think you brought with us some of the science for us to learn that you've been learning and researching and finding out for yourself. So I think you brought a few slides.
I did. Yeah. Are we ready to share the screen?
Yeah, let's give it a shot. Let's see some of these pulsar wind nebula, which
Yes.
we've touched on in a couple other talks, but I'm excited to see your perspective on it.
Yeah. So let me go ahead and share my screen and I'm going to share this one. So hopefully you can see my Google presentation. Yeah.
Let it load here. Make sure it comes out. We can see your screen, but it's loading right now. So
okay. All right, cool.
Perfect. Now we can.
Yeah. So this is something that I have really started working on extensively at the Harvard Smithsonian with you all. And this isn't like the first research project that I've ever done, because I did start something very similar back at Clemson, but then I pretty much dropped that once I got here and I was like, I'm going to work on this Pulsar Wind Nebula catalog. But I'm going to focus today on what I'm working on now. And so that's Pulsar Wind Nebulae. And I will tell you guys what that is. But I do really like this little image right here. So this, can you guys see my mouse?
Yes, we can.
Okay, cool. So this telescope right here, this is the Fermi-LAT. So Fermi is just a really famous scientist's last name. And we ended up naming this telescope after him. And the LAT, it stands for Large Area Telescope. So the Fermi-LAT, so Fermi Large Area Telescope. And, okay, spoiler alert. So the Fermi-LAT is a gamma ray space telescope. And gamma rays are the highest energy forms of light. So they are, if you are thinking about, I probably should have gotten an image of the light spectrum, but if you've got your radio waves over here, then your gamma rays are way over here. So, very harmful for humans, but don't worry, they don't get through our atmosphere, so we're good. Which is actually why we have to look for gamma rays using space telescopes, is because the gamma rays they do decay in our atmosphere. So we have to be able to have space telescopes up in space so that we can actually see gamma rays that are coming from sources that are not in our solar system. Although the sun does gamma ray emit, but I'm not interested in the sun. I'm interested in pulsar wind nebulae. So pulsar wind nebulae are attached to pulsars, and pulsars are attached to supernova remnants. And so all three of these items descend from a core collapse supernova explosion. A core collapse supernova explosion occurs when you just have an isolated, really massive star that's at least 8 solar masses. And at the end of it,
solar masses, you mean 8 times the size of our sun, correct?
Exactly, yeah, 8 times the mass of our sun. So really, really massive star. And at the end of its life, it explodes. And so when it explodes, it creates a shock wave that is moving really quickly out into space. And so this thing creates a shell, because as it moves out, it sweeps up material. And so it will sweep up the material and heat it in a way that we can actually see it across the wavelengths. So any form of light, really, from radio to gamma rays, we can tend to see this depending on how long it's been expanding. And so that's what we call the supernova remnant. And so that is what I'm showing you in this little cute GIF right here, is that you're seeing the star explode, and then it's sending a shockwave out into space. So that would be the supernova remnant. So for core collapse supernovae, it will also leave behind a really dense core of a star. And this core is very neutron rich. So we sometimes call it a neutron star for that reason. And because it has collapsed so violently, it is born rapidly rotating. So it is spinning super, super quick, like on millisecond scales. So sub-second scales, and you're seeing these pulses of light every time that these stars will rotate towards us, because they are just so powerful. They are radiating across the spectrum as well. And so when we see these pulses of light at Earth, which is much like how a lighthouse works, you'll see it every period, you'll see these pulses. So we also sometimes call them pulsars. So neutron stars, pulsars, and whatever you want to call them, they're the same object. So the neutron star will lose its energy by forming a pulsar wind nebula. And so that's what I'm really interested in.
Can you go back for just a second?
Yeah, absolutely.
Just for our audience who might have missed one of our past talks, the jets that are coming out on either end are actually coming out at magnetic poles, correct?
Yes. So much like the Earth. So the Earth has a rotational axis that is pretty aligned with its magnetic axis. And so we have a very similar orientation that we have with pulsars as well. And because the pulsars are so energetic, they will often spew material that will ride along the magnetic poles, because that's where the magnetic fields are strongest. And so you see these beams of light, because as these particles are interacting with the magnetic field, it creates this really intense form of light as these jets are moving along the magnetic poles. Yeah.
Great.
Or the lines that are coming from the magnetic poles. And so this is an image of an actual pulsar wind nebula. And so okay, let me use my mouse. So this little dot right here, this is the pulsar. And so everything that you're seeing around it is the pulsar wind nebula. So the pulsar is generating this. And in the blue image, this is an X-ray image. So Chandra, who is technically funding me, a Chandra X-ray space telescope. X-rays also get absorbed in the atmosphere, so Chandra has to be up in space as well. And so this is, oh goodness. Okay, sorry. My mouse is just
a little sensitive this morning.
A little bit. And so Chandra took this. It is not a movie. It's just stacked X-ray images over time that they made a movie with, because we actually don't see this type of movement that quickly. And then in the orange picture, we're looking at the optical wavelengths, and it is also stacked as well over, I can't remember what the time frame is. But this is a pulsar wind nebula. It's a very special pulsar wind nebula. It's called the Crab. It's the most well-known, most studied pulsar wind nebula like in history. So we have lots and lots of data about it. And yeah, just pulsars are, these are just really amazing. And we have lots of relativistic particles that are responsible for the radiation that we see across the spectrum. So including the X-ray picture you're seeing here and in the optical. And so that's really what I'm interested in. I want to know how the particles are radiating. How are they being stripped from the pulsar and accelerated into the nebula? And I'm also interested in how the nebula changes with time. So what stages does it go through as the pulsar spins down and loses more energy? So that's really what I'm interested in. And here's the famous picture of the crab, just so that people, I don't know, I think that this is maybe a really famous photo that people might be like, oh, that's what she's talking about. This is the famous photo of the crab. And so right in here is where we would see that nebula.
Right. So this photo is in other wavelengths of light compared to what you're looking at in the pulsar wind nebula.
I think so. I would actually have to look up.
Well, it has to be, right? We're not seeing the details of what you're seeing in X-ray, correct? So if we were seeing X-ray, we would be looking at X-ray.
Right, right. Yeah, I do think that this might be adding together different types of wavelengths, but I don't know off the top of my head.
I do. It is. Because one thing I'll let our audience know is you can actually take your own picture of the Crab Nebula using the microobservatory telescope. Yeah, it's pretty exciting. And you can actually, ours, obviously, this is a telescope in space that took this. I believe this is a combination of Hubble, maybe some Spitzer data.
I think so, yeah.
And so ours is not like that, but you can still get your very own image. If you request an image, you'll get your very own back. And you can actually create an RGB, which is using multiple wavelengths of light to create an image. So you can actually look at that with the Crab Nebula using microobservatory. So
awesome.
Just gonna throw that little plug out there for our audience. They can study the same objects in space that you're studying.
Yeah, that's awesome. I think I don't know if I'm allowed to give homework assignments to anybody who's watching, but I think that would be really cool. And then maybe people can share their results using that hashtag Astro Chat, or I don't know if that would be confusing. Maybe there's another hashtag we could make for that, but that would be really cool.
No, share it using hashtag Astro Chat. Let us know that you're, doing these things as part of joining us. So we'll comment on them. We'll let you know what we see with them.
Yeah, and then I have like more stuff, but I don't know how advanced it would be. These are preliminary results that I have. What do you think?
Well, let's start and we'll see where we go. We'll see if I'll ask questions, lots of questions, so that our audience and myself can understand. I don't know if I've told our audience this. So my background is actually not in astronomy. I have become very interested and I spend a lot of time learning about my colleagues' work, but my background is actually in biology and education. So I spend my time trying to figure out what our scientists are saying too. So I'll ask a bunch of questions and they'll be for you, but they'll also be for me.
All right, cool. Well, yeah, I'll definitely try to break this down with everyone, just to kind of show you like what is involved in being a graduate student researcher, particularly in high energy astrophysics. It does change quite a bit depending on what exactly you're researching, even down to what source you want to look at. That could even change a lot on what wavelength you want to look at, and other things like that. So, but for me,
when you say high energy astrophysics, you're talking about looking at high energies of light, right? High wavelength.
Exactly. Yeah, I think the consensus is that anything with higher energy above UV light would be considered high energy astrophysics. For me, I specifically look at X-rays and gamma rays for the most part. And yeah, I think that would be a good way to describe that. And so with the Fermi-LAT, I'm interested at imaging all pulsar wind nebulae that we know about in other wavelengths. We have lots of information about pulsar wind nebulae, particularly in the radio regime and the X-ray regime, so the lower energy X-rays, which we call soft X-rays sometimes. And so we have lots of observations in those regimes, but we don't have a lot of observations of pulsar wind nebulae with the Fermi-LAT or in that energy range at all. So the MeV to GeV range, which is just the units of energy, which would correspond to the gamma ray range. And so I want to image all of them with the Fermi-LAT. And I'd also like to search for new pulsar wind nebulae around other pulsars. So, but first, what I've been doing is working on a technique to try to establish so that I can have a nice generic method that I can apply to all these objects, because there are over 100 of them. So that's a pretty big task. So I need to have something really, really.
You want a standardization, right? You want to be,
yes.
You want to look at everything this in a same pattern so that when you have that data afterwards, that you know you've done all the same steps for all of these objects.
Yes, pretty much. And so I'm just showing one energy range for the first source that I used to establish this technique. It's called MSH 1556. It is what you would call a composite supernova remnant. So you have the pulsar, the pulsar wind nebula, and the supernova remnant. So all of those are visible in many wavelengths. And it turns out that this particular object will gamma ray emit both by the supernova remnant and by the pulsar wind nebula. And so this was an interesting thing to learn, how to basically, how do you differentiate what's coming from the remnant and what's coming from the nebula? But it was still, it's still very easy to figure out based off of previous research with people studying these objects, how to deal with the different gamma ray emitters in this region. So to get into some of the stuff, these are data products that I plan to make public and free for anybody who wants to use the Fermi-LAT Pulsar Wind Nebula catalog. This is going to be available on a website for anybody to look at. And so these are the type of data products that I'm going to be showing. So on the left panel, I'm showing a counts map. And this is just showing you all of the photons in this boxed region. So this is just 1 degree by 1 degree across. To put that into perspective for everyone, the moon is about half of a degree across when it's in its full moon phase. So the region of sky that I'm actually looking at would be 2 full moons by 2 full moons. So that's basically what we're looking at here.
And I think you were almost doing it. My favorite way to understand how much that is actually if you hold your arm out full length and look at your pinky nail. That is about 1 degree of the night sky. So if you blot something out with your pinky nail, that's about 1 degree.
Okay, perfect. Yeah, so people would just go and do and that would be equal to what I'm looking at here. So it's a fairly small region of space, but we're able to look at smaller than that with lots of telescopes. So that's pretty exciting. But anyway, so it's just a counts map. It's just showing you all the photons there. It includes background emission, so things that are not coming from the pulsar wind nebula. Another caveat of having to deal with these objects is that they lie on the galactic plane. So there is a lot of noise coming from dust and stars and other supernova remnants that are all along this region. And so you're getting all of those counts in this image as well.
And for those of you that haven't joined us in the past, the galactic plane, you've seen those beautiful images of galaxies before, right? And they're all spirally. Imagine looking straight through that like it was a CD. The galactic plane is the flat part. So instead of looking up or down, you're looking out through that plane of all the stuff, just to help our audience. And one thing, because I'm going to take a moment here just to talk about microobservatory again, is we have an image analysis called JS94L that you can start to learn about some of these things that Jordan's talking about, our image analysis allows you to do the same colorization of objects of the night sky. So you can take your own image of the Crab Nebula, for instance, and count how many photons of light fell on each pixel. It won't be as high quality images as Jordan's talking about, but you can start to do similar things like as that. So you can get your toe into learning what Jordan's doing.
Yeah, that sounds great. I'm glad that there are all these tools out there for people. But yeah, so that is a counts map. And where you see this green circle, that is what the supernova remnant size is in the radio wavelengths. And so we kind of do stuff like that just to get an idea of what emission might be coming from the supernova remnant itself. So taking what it looks like in one wavelength and then superimposing that onto an image that you got from another wavelength, that can give you a good idea of maybe how the shape is going to change, and what type of emission you can associate to the same object that you're interested in. And so this is just the size of this of the remnant's radio size. And then these like wiggly black lines right here, these are called contours. And this is simply just showing you the shape of the Pulsar Wind Nebula in the same radio band of where I got this radio size for the remnant. So this gives you another good idea of where the Pulsar Wind Nebula would fall and where its peak would fall. So you can kind of tell how that might coincide with the gamma ray emission. And then this PSR, that is just standing for the pulsar that is associated with this remnant. It is not a gamma ray emitter though, and it is right here. And then the PSF that you see, this is called the point spread function. And this essentially is telling you what the angular resolution is. So the angular resolution is essentially like, you know, if you had two point sources next to each other, how well could you be able to see that they are 2 point sources and not just one blurry point source, basically. And so the PSF here is about a 0.1 degree. So, you know, you can imagine taking this difference and saying, okay, so that's 0.1 degree. So that's just kind of there to give you guys an idea of how well the telescope can see all of this emission.
So like, sure. If our audience was looking at night in a field at two light bulbs on the other end of the field, that's how far apart would those two light bulbs have to be able to tell that they're two light bulbs instead of one?
Right.
Okay.
Right. And so the TS map is what this like pixelated guy is. This might be a little bit too advanced because it does have a little bit of statistics involved. But essentially what a TS map does is I tell it to look for a point source. And by the way, when I say point source, I just mean like a point of light, as opposed to an extended source, which is certainly what this Pulsar Wind Nebula is, because it's not a point source. So anything that has extended emission, diffuse, isn't just a ball of light, would not be considered a point source. So anyway, the TS map measures the likelihood of a point source being somewhere at some location in the field that I give it versus there being a point source. So when you have a TS left over that is very large, say like 25, then that means that there's a big likelihood that there is a point source there and it is emitting in gamma rays. So where you see this red pixel here, that's the highest TS value. And it is somewhere around 80. It looks like, I'm just reading off this color bar, so somewhere around 80. And so a TS max that high means that there is a significant chance that there is a point source emitting there. But the fact that you also see these high TS values around the red dot, this tells you that it's likely that the point source being here is also not just a point source, it's got some extension here as well. And so this is basically showing you that in the 300 MeV to 2 TeV range, which is essentially the full energy range that Fermi-LAT can look at, that the Pulsar Wind Nebula is there and it's extended. So that's pretty much what that is showing you.
So when you gave those ranges, you just mean wavelengths of light, right? Energy light. There's many ways of talking about light and energy.
Yes. Sorry, what was that? What did I say just before?
So you gave us a technical number for what Fermi looks at.
Mhm.
And I just want our audience to also know that that's also a wavelength of light.
Right. Yes. And we use MEV and 2T and TeV and stuff like that, and that is just a unit of energy. And so the the like standards that people use, it depends on whether or not wavelength, energy, or frequency is more convenient way to describe their wavelength range, really. And so the gamma rays have really small wavelengths and really high frequencies, so we just use energy ranges. But yeah, so this is only the gamma ray range, the 300 MeV to 2 TeV.
Okay. And actually, thank you for making that comment, because I think we haven't really spoken about that yet on any of these Astro Chats yet, that there's many ways to describe and talk about light. And it can get really confusing, depending on what scientist you're talking to might depend on what terms they use. And as you learn about light, you're going to be confused for a little bit, but that's okay. Uh, light's a confusing thing to understand. There's many aspects to it and different for understanding. So
Yeah. And when I joined the graduate school, I had very, very little experience in particularly high energy astrophysics. I did some stuff with radio, but even then it was like very, very basic stuff. So I remember being really confused on why people would describe it as soft X-rays versus hard X-rays. And nobody really describes what they mean by that. But so if that does come into play at some point with these talks, just know that when they say soft or hard, they literally just mean if it's on the low energy. So low energy side of the X-rays would be soft, but then if they're higher energy X-rays, they're called hard. So there are definitely issues like that where it just becomes such common like slang, I guess, that nobody feels the need to describe it. Um, and so for months, I was just like, what does that mean? And I felt stupid for asking it, because I was like, obviously everybody knows what it is, but
right, and I think that's a really good point. Like, there's a lot of questions that you can feel stupid asking because it's in the know for a group, but that doesn't mean it's obvious. It just means that group has been talking and using that term for so long that everyone just kind of forgets that new people to the group don't know.
Exactly. Yeah. And I mean, even I have hard time doing that now. Because I don't know if this is above everybody's like pay grade when I talk about stuff like this, but everybody's welcome to contact me outside of this to ask me what the heck was I talking about? What do I mean? And I also don't know how much time do we allot for presentations? Am I doing too much?
No, you're fine.
Okay. Well, I mean, I honestly, I'm not even sure like how much I wanted to talk about everything. Let's see. So I am interested in cosmic rays as well. So let's talk about that a little bit, because it's very related to pulsar wind nebulae. So let's see. This is another complicated plot though, but I'll try to walk everybody through it.
Well, maybe instead of just walking us through it, you could walk us through how, if you were to come across a plot like this, you would start analyzing it too. Because I think that's a skill that a lot of scientists have. And when you don't have that skill, you see something like this and you're like, oh my God, I could never understand that. But there's a process for starting to understand what a plot like this might tell you. And even if it's outside of your field, you can start to look at certain things to better understand. So maybe as you walk us through it, you could also walk us through how you would approach new plots like this.
Absolutely. Yeah. And this is honestly another thing. Is that these types of plots are very confusing to look at. And I did spend about the first year of my graduate school experience trying to figure out why we plotted a certain way. I recently did a blog post, though, actually explaining why we do things a certain way. But I'll also touch on that right now. So cosmic rays, first of all, I'm interested in cosmic rays. This is a really big question in high energy astrophysics because they are high energy particles. So you have particles of light, which we call photons. They travel at the speed of light. It has been recently detected on Earth that there are particles that are not photons that can travel close to the speed of light. And this is a really unique thing because they obviously must have gotten such a huge kick of energy from somewhere. And we really want to understand where that somewhere is. And this question ties in to pulsar wind nebulae because they are some of the most extreme objects that are in our galaxy. And so theoretically, it would make sense for the bulk of cosmic rays that we have seen and detected here on Earth to be coming from something as extreme as a pulsar wind nebula, as well as supernova remnants. So those are the two guys in our galaxy that we believe are responsible for the bulk of galactic cosmic rays that we see on Earth. And this plot that you're looking at, this is data that we have collected from Earth. So these are cosmic rays that have bombarded our atmosphere and cascaded and turned into some other interesting particles and astroparticle physics going on that would allow us to detect these with various ways. So you see all of these data points, they're coming from a dozen different experimental labs, or not experimental, observational labs. And so they are actually getting this data. They're able to detect and reconstruct the paths and try to understand what particle was responsible for this radiation that we then detected. And so it turns out that protons, you see that protons are up here, protons actually make up most of the cosmic rays that we see. So they travel really, really fast. Then they bombard the atmosphere and they decay, and it causes like a shower of radiation that we can detect. And so about over 90% of the cosmic rays that we detect on Earth are made up of protons. So that's a big question. Where are they being accelerated? Where are they being formed? And then how do they get to Earth is another really, really hard question to answer. So on the y-axis, this has some funny units, but we're just going to call it the flux. I mean, that is what it is. It's the flux. So how much how much energy does this particle have when it comes and hits the atmosphere? And then on the x-axis, we have the energy. And so you see different contributions, and these are all data points. So we have protons contribute the most, then we have electrons right here, positrons, and antiprotons here. So these are all contributing in some way to this all particle curve, this black curve right here. And we can model this curve to try to understand its spectrum a little bit. So this is what we would call a spectrum, is the flux versus the energy plot. And so we see this like tiny disconnect right here. And this corresponds to about 10 to the 7 GeV. And so we believe that where we see particles that are having energies less than that right here, so anything less than this, like right here, we think that that's coming from supernova remnants and pulsar wind nebulae. And so that's a kind of an interesting, well, it's a really interesting question in high energy astrophysics. And so I'm hoping to also be able to touch on, or at least provide data that can help us understand what is the likelihood that pulsar wind nebulae are contributing and how much, and how are they generating cosmic rays. So that's another really cool thing. Very interesting phenomenon that I've just become obsessed with.
All right. So thank you for walking us through that. I'm just going to make a couple points for our young audience because we have everywhere from middle school to high school to even some college students. The protons, electrons, positrons, and antiprotons, those are big words. You may or may not have started to learn about atoms and the particles that make up all of the universe. If you haven't, those are just some of the smallest things, not the smallest, but some of the smallest things that make up everything we can see and observe and feel. So atoms might be the first thing you'll learn about. Inside atoms are protons, electrons, and neutrons. And so these are just the teeniest, think of them as the building blocks or Legos of the universe. So those are just the names for those. Just want to throw that out there because you may or may not have learned about those yet, and that's okay. Those are, you know, each step. I actually didn't know about antiprotons. So
I know very little about them, I will admit. Specifically, I will say that if you guys think of protons and electrons, that's pretty much what makes up a lot of elements that you guys might be studying right now. Like hydrogen has 1 proton and 1 electron. So maybe that'll help people connect that a little bit. Positrons and antiprotons are a little bit more complicated, but they're kind of, they're similar particles to protons and electrons. So
they're just things that build our universe. So I just want to throw that out there. But you did a really great job of kind of walking us through these different things.
yeah.
And just a reminder, GeV is just one of the units of energy, right? It's the name for that particular type of energy. So you might have learned about watts in classrooms, just a different type of energy and a different unit for that.
Absolutely, yeah. You can convert GeV to calories if that helps anybody and visualize that, because calories is just a unit of energy, and so is GeV. When you have a capital letter in front of the EV, that's just giving you a type of unit like 10 to the 6 or 10 to the -3. It gives you an indicator of what units we're talking about, really. So yeah.
And yeah, so you did a really great job of walking us through how we might start to understand some of these. Obviously, we're not all going to know what all of the numbers and equations stand for, but you can start to understand how somebody might go about looking through that. So thank you for walking us through that.
Yeah, I mean, it's a lot to unpack. I mean, even now when I look at something like this, I have to stare at it for a while to really understand what all is there. So it's not an easy thing. Like, and I apologize honestly for showing everybody that, because I feel like that just maybe made everybody's head spin.
But hopefully it also means when you go back to class and you've got a bar graph or another graph that you're starting to look at, you can think of it in a way that, how do you start to understand that data in the graph that you're looking at in class? It might not have as many complicated details as the ones that scientists like Jordan are looking at here, but the more you understand the ones that you're looking at in class, the more you'll be prepared for later.
Yeah. So. Yeah, just always taking your time to like look at a plot. Because I mean, I might be, an expert in my field, but like sometimes it takes me, 10, 20 minutes really to even look at a plot and be like, what are they showing me? And what does it mean? That's something that I don't think any type of expertise will make that go away. It's just kind of what comes with understanding and interpreting data. Yeah.
Yeah, it's a process.
It's exactly.
So I think we've got about 15 minutes left. And I'd like to ask you a few questions and remind our audience out there that they can ask questions too using the hashtag Astro Chat.
Go for it.
Yeah, so maybe we'll stop the sharing for a little bit. And I'm going to ask you kind of some more questions about yourself. So you already told us, I usually ask if there were any classes you struggled with. You already told us that. Were there any classes that you really loved in middle school or high school?
Honestly, no. That's another thing that I've pondered, as I've grown up and really reflected on that. Because I feel a little bit, I don't want to say cheated, but I didn't have the high school or middle school experience that I feel like a lot of other people had. Like they had a mentor teacher, that they really loved and bonded with, and they would go back after they graduated high school to go say hi and stuff. And like, I never felt that way with any of my professors or teachers. And really, there was no class that stuck out to me. I was very uninterested in school. I didn't even think seriously about college until everybody else was talking about it. I was like, I guess that's something I need to go, like, So it was a very normal high school experience. Like, honestly, it's anybody who knew me in high school is like, holy crap, like, how did she end up where she is? So, yeah, I mean, and I just hope that if there are other kids out there who feel like that, like they're not having a special bond with any of their teachers, it doesn't mean that you're not special or academically inclined. It's just, it's just how it is. You can still do amazing things.
Yeah, yeah. Just because traditional school, as we know it right now in middle school and high school, isn't something that you immediately connect with, or that you feel like, this is my thing, I'm really good at this, doesn't mean you can't be successful at things that might still be academic later in life, right?
Mhm.
Often we think, oh, if I'm not good at this, I'll have to find something outside of academia later. But if there's some a topic that you're really passionate about, that's okay. And there are ways around that. It does require lots of work, like you've mentioned, right? You have to be prepared to put in the effort. You can't just all of a sudden be there. But
Right.
if you're willing to put in the work, you can find those things and still be successful at those things.
Yeah, absolutely. And I really like that quote where the people are like, what do they say? Um, don't be worried about the time it takes to do something because that time will go by anyway. So that always resonated with me because I was like, oh, they're so right. You know, if you're like, oh, it takes me 4 years to get a bachelor's, that's so long, but it's like those 4 years are going to go by anyway. You know, don't you want to be able to be productive, do something to better yourself? You know,
Yeah. And do something you're interested in.
exactly. Yeah.
Yeah. Um, so what if you had any, what careers were you interested in when you were younger?
I did explore a few. I always really liked Spanish, so I really wanted to learn. I mean, I still want to learn Spanish fluently. It's honestly kind of pathetic that I've been learning it pretty much my entire life and I still can't speak it fluently. So it's still a goal of mine. And I wanted to become like trilingual. At one point, I really wanted to be a CIA operative. I know that sounds silly, but like I really wanted to be a spy. So I was looking into like doing international affairs as a college major. And I also really liked like entertaining. So I really liked singing and I wanted to be an actress when I was like in middle school. That kind of fizzled out a little bit. So it was like unrealistic. Also turned out I had stage fright. I did take a drama class and it was awful. Um, and so I explored around with like linguistics and language. I thought about psychology. I still think psychology is really cool, but yeah.
Awesome. Yeah, I think it's good to showcase kind of the different types of careers people have been interested in.
Yeah.
Um, so I think you've shared a bunch, but maybe I'll give you an opportunity in case there's something else you want to share. What's one thing that might surprise people about you, particularly in how that relates to being a scientist, somebody that shows us plots like that? What might be something that would surprise our audience about you?
I think it might surprise people. Um, I think it might surprise people that I'm kind of a girly girl. Like I don't really think people picture physicists as being you know, like right now I'm wearing fake eyelashes and I love to get my nails done. I love to do my hair and I just don't feel like people really expect that from a physicist. I feel like maybe even people are a little bit surprised that I'm a girl. um, and I mean I really enjoy um dressing up and being a girly girl. I feel like people might be thrown off by that, but I've come to terms with it, honestly.
No, I think that's great. I think a lot of times, and historically, it was difficult for women to be girly girls in science fields because of the history and it being so male dominated. But I think today that's shifting, and it is more acceptable for a woman to be both, a respected scientist and a girly girl, a quote unquote girly girl, right? That you can have both, be both of those things at the same time, and I think it's great to showcase that. Oftentimes, I think young girls who consider themselves girly girls think, oh, well, then the science isn't for me because I'm interested in dressing up and putting on makeup. Therefore, that field isn't for me. And I think it's great to kind of point that out that you can be both.
Yeah, actually I think that was a great point that you made that like I've always kind of been worried that maybe I wouldn't be taken seriously if I, you know, dressed too girly or something. I mean, always be professional. I mean, I think that those rules have laxed up a little bit. not that to be like a little bit more casual is totally okay. But I've always been a little bit weirded out, like maybe somebody's gonna like assume I'm stupid or something because I look a certain way. But I've come to terms with that. Like if somebody wants to judge me the wrong way, they can, because I'm a really hard worker and I feel like I will prove them wrong in the long run. So
Absolutely. uh, so speaking of proving people wrong about what you know, we've got a couple science questions for you.
yay.
So one is, besides the Crab Nebula, do you know of any other nearby pulsar wind nebulas that are large and bright enough to be seen with amateur telescopes?
Ooh, with amateur telescopes, I would have to do some research to see how bright pulsar wind nebulae can be in the optical. That is a really good question. You might even be able to Google visible apparent magnitudes of pulsar wind nebulae. But I can think of several very large pulsar wind nebulae that are like specifically the Vela pulsar wind nebulae. It's like 2 degrees by 3 degrees in size. And it's actually the closest composite supernova remnant to Earth. I think it's even closer than the Crab Nebula. And I don't think you would be able to see that one in the optical though. But that is a really good question. I would have to look that up. Yeah.
Maybe if you've got some free time, you can do that and share that with us, because perhaps there's another one other than the crab that we can look at.
Yeah, that would be awesome. Oh yeah, I'll have to look that up. But in terms of amateur astronomers who might just be, using their telescope and wanting to see something, I would have to look up and see if pulsars are visible in the sky. I'm not sure if that's a thing. I think the crab pulsar was really bright at one point, because I think Jocelyn Burnell said something in her talks, if you ever remember her saying that somebody noticed a flashing star a while back. So I'm not sure. I'll have to do some research on that. That's a good question.
Right, yeah, because she mentioned how, Dr. Jocelyn Bell Burnell is a really incredible scientist, very well known in the astrophysics field. You should look her up. She's inspirational. But she gave a presentation at the Center for Astrophysics recently and mentioned that somebody observed it with their eye, but nobody believed it at first, because it is, I think she mentioned, young and very good eyesight to be able to actually differentiate the pulsar. Now, that's not to say you can't see the other aspects of the nebula, but the pulsar aspect of it itself would be very difficult to see with the naked eye.
Although I will suggest the Orion Nebula, although it's not up right now, but the Orion Nebula actually is visible in the northern hemisphere in the winter times. Its magnitude is like 4, and humans can see up to 6. So maybe jot that one down for the future. It's not a pulsar wind nebula, but it is it's a stellar nursery, I think. So
absolutely. So I got a question, and I think I'm gonna narrow it down just a little bit. So why did you choose high energy astrophysics to focus in? So we kind of got your story into physics. What was the next step? How do you make the decision for your next step?
Yeah, so I chose physics because I liked astronomy. I really wanted to get into radio astronomy because of the movie Contact, which I talk about so much, but it's like 30% of the reason why I'm here, to be completely honest, because I really did idolize the main character in that movie, and she was a radio astronomer. So I really wanted to do that. I wanted to work at, the Very Large Array or something like that. But when I got to Clemson, it really came down to what my options were, like what type of research professors were doing. And so just kind of, interviewing each one of them and trying to figure out what type of research do they do and what they offer. And actually, even then, I think I was more interested in dark matter. So in undergrad, I was really interested in radio astronomy. At some point, I was like, I want to learn more about dark matter. So then I went to Marco Aiello, who is my Clemson University advisor today. And I remember asking him about dark matter, and he was like, yeah, it is, it's pretty popular among the gamma ray astronomy community, because this is one of the areas where people try to search for dark matter. And so I got involved with that, although I don't do anything with dark matter. But he gave me a research project, and it was related to pulsar wind nebulae, and I just loved it. I loved doing the analysis, and programming and everything to get these pretty X-ray images. That's how it started out, at least. And I really enjoyed that. So I just kind of stuck with it.
Great. I think that's great. One thing people don't realize, I think, is to go talk to different professors, different researchers, and figure out what they're doing, because that's a great way to learn what you might want to do. Send emails. Go visit.
Yeah.
When we're allowed to go visit, go visit.
Yeah, exactly.
So I've got two final questions here. One is kind of a fun one from our audience that they've been asking recently, and I think it's a fun one. I think you'll enjoy answering it. Would you like to travel to the moon or Mars?
I've been asked that question with planetarium shows, and I would visit the moon, but not Mars. I don't think we would be able to come back to Mars or Earth. Depending on how much time you spend at Mars. I'm not really sure what the science says on that, but I am concerned about how Mars's gravity is like half as strong as the Earth's. So I do have some concerns on what my body would go under if I were to go to Mars and then try to come back to Earth. I'm not sure how much time you would have to spend on Mars for your body to get used to that gravity, so that if you were to come back to Earth, your body would just get crushed underneath Earth's gravity. I'm not sure what the science says about that, but that's one of my main concerns. So I would have to say no with Mars. If I were to go into space, I want to be able to come back to Earth, because Earth is my favorite planet.
It's a pretty good one for living on.
It's a pretty good one. I mean, we've got water, like lots of it.
Air to breathe.
Yeah, 4 seasons.
Yeah, I do know it would be a minimum 3-year round trip.
Yeah.
Just, get there, figure out how to do it, and then get back. And that's assuming we could carry everything to get ourselves back, because that is one of the challenges with Mars right now, is we could maybe get there, but to carry enough propulsion to get ourselves off and back would be very difficult. So yeah, I agree. Those are kind of things that would limit my want to go to Mars as well. All right, I've got one last question before we round off the day, and I remind you about other opportunities to join in. What's a piece of advice that you would give someone who's interested in astronomy or any science or STEM career, technology, engineering, math, a young person that's maybe in middle school? What's one piece of advice you would offer them?
My first piece of advice would be to relax. You have plenty of time to figure out what it is that you want to do. Just pay attention to your own interests and pursue them how you see fit, whether that's like a video game or a computer game or reading, or watching vlogs, which there are, there's lots of stuff for you to figure out what kind of hobbies you like to do online. And there are lots of electronics projects that are super affordable that you could ask your parents to buy you for a birthday gift or something. And you just start experimenting, but don't feel at all like you need to go a certain path in order to get where you envision yourself, especially since you guys are in middle school and high school for the most part. You really do have all the time in the world. Even if you're a senior in high school and you don't even know if you want to go to college yet, like, it's okay to just sit in your little uncertainty bubble for a while and figure out what it is that's truly important to you. And when you have that, when you think that you have that thing that you really want to go for it, just do it. Go hard, like really commit yourself to it. If it stresses you out and makes you feel horrible, consider doing something else, and don't make yourself feel bad for that, because you should be happy with what you do. But also recognize that anything worth doing is not going to be easy. So you will have your bad days. I have cried plenty of times when an analysis was not working, or I kept getting a weird error. Things will still go wrong. So, don't give up so easily. I gave like 10 pieces of advice right there.
Oh, but those are all great pieces of advice. I think those are all valuable things for our audience to consider, going forward. So thank you for all of those.
Yeah, yeah, I mean, I hope that you guys learned something today and enjoyed it.
And I want to give you a second because you mentioned it. I want to let people know that you write a blog about
Yeah,
science, right? And
yeah. I mean, if there's time, I could actually like just preview it just a tiny bit.
for a minute, we can run over a couple minutes.
So I will just do this really quickly because I did make a slide. But guys, if anybody is interested, I do have a blog, and it is very research based. It is jordanleagle.com. And if we click there and go to it, yes, recently I did do a DIY haircut, but it is mainly research. I share lots of thoughts. I walk people through my master's thesis. It's very educational based, so I really try to break down a lot of concepts. I even go through like my life story. So like, how did I get where I am today? How much did I actually suck in high school in terms of science and math subjects? I offer like grad tips, self-care, mental health. It's really a wide range of things, but if you're really interested in following the research, there's a blog tab that is just research. And again, it's educational based. And if there are any questions, there is a contact me form. So even if it's from today, I would love to hear from people. I am all about sharing my science and trying to get people interested and to understand it. I know that it's like a mouthful of stuff that I said today. So, I mean, just whatever it is, people are welcome to reach out in any way.
Thank you so much. And thank you for sharing your research with us today and kind of your experiences in astronomy and school. I think we learned a lot and got some really great perspective from you today. So thank you so much.
Yeah, thanks for having me, Erica.
Yeah, our pleasure. And thank you out there for joining us again today and for asking your questions. As I said at the beginning of today, it's actually a double header day. So join us back in 3 hours at 3 p.m. Eastern with Daniel Castro. We'll be talking about the explosive death of stars. So
Oh, he's my advisor, by the way, you guys. He's the one in charge of my Pulsar Wind Nebula project.
so I didn't even realize that. I should have looked at it. That's perfect. So maybe this morning will be a primer for what he's going to talk about.
Exactly, it's perfect.
This is a perfect double header day. And here I was missing that whole point. I do my best, guys. Or we can say that I did this on purpose. I definitely plan to have you guys go on the same day.
Well, it works out.
Oh, great. Yeah. So join us this afternoon and we can talk to Jordan's advisor and learn about his perspective on Pulsar Wind Nebula and the research that he's doing with it. So that's so perfect. Join us and come back in 3 hours. And thank you again, Jordan. This was fantastic.
Awesome. I'd love to be back whenever you do this again. You just let me know.
Awesome. We will. Thanks again.
Bye, Erica.
Bye.